All right. Today we're gonna finish up optical properties, and in doing so, we're gonna talk about fiber optics. So that's gonna be the central theme of today's modules. So first, let's talk about total internal reflection. All right. So in a fiber optic system, the overall entity is called a waveguide because we're trying to guide a wave through a fiber. And so this whole idea is based on the principle of total internal reflection, sometimes abbreviated TIR. Okay, and so the idea here, like we've seen a couple times, is that we have two different, in this case, glasses of different indexes, and that's the refractive index. Um, so in this case, we have a high index glass that is completely surrounded by a low index glass. And we're going to see what this does, right? So we have the angle here, phi, between the normal to the interface and the angle of the light. So basically the arrow here is the light inside the waveguide. And then afterwards, it's phi prime when it goes into the low index material. So if we keep changing the angle here at which the light is relative to the surface of the interface, then at some point we get to a point where the incident light, reaches a critical angle. So in this case, phi C. And so at that point, it's critical because at that point it is reflected. So instead of merely bending the light into the low index material, it actually reflects the light. And so we now have the light that bounces off the surface and comes back at the same angle. And so we call this internal reflection. And so the idea is that it is completely reflected within the waveguide system, and therefore you get the term total internal reflection. All right, so let's see the components of the fiber optic waveguides that actually make this happen. So we're gonna have a light source. That's where we get our light. We're going to have a core material. That was the high index glass that we talked about in the last example. And then that high index glass, which is typically a fiber, is surrounded by a cladding material, and that's the low index glass. And then beyond that, there's often a jacket or something basically protective, like a polymer coating on the outside, just to kind of protect the whole system. So that jacket or coating on the very outside, we're not going to sort of evaluate that in terms of the internal reflectance. That's just more for processing and for overall upkeep. All right, so the total internal reflection that we saw is going to be governed by Snell's law. This tells us what the critical angle is going to be. So again, in this example, we're using theta instead of phi, but the same idea is true. We have a material. Here, you can ignore the water. This is just the high index material, the low index material here. So for the core, the index of refraction is N1. For the cladding material, it's N2. In this case, we have an incident ray at angle, in this case, theta 1 with respect to the normal, and then it is refracted at an angle theta 2. So basically, at the critical angle, we can think of it as being refracted, and so that's the critical angle at which that happens. And so this is where we have total internal reflection. So theta 1 equals theta 2. So here, down here is Snell's law. So this is N, so the refractive index of the core times the sine of that angle is equal to the new refractive index of the cladding times the sine of the angle for that. So essentially, this is theta 1 up above, this is theta 2, and then N1, N2. So there's some changing nomenclature because of where I got the figures, but I will try to keep what is consistent with the book for the equations. So this is Snell's law, and the way we can get critical angle is by setting the second angle, phi prime, to 90 degrees. Because essentially, if you look at this example here, if we think of this light that is parallel to the fiber, that is going to be 90 degrees to the normal. And so we can set this to 90, and we get that the sine of that critical angle is going to equal n prime over n1. So this is n of the cladding over n of the core. So that's how we can get our critical angle. All right, so let's just run through a quick example of this. And I'm going to use a couple materials that we've seen before. So a lead-based glass for the core and a cladding material made of soda lime glass. So these are two materials we talked about when we talked about the various amounts of reflective behavior, right? So we'd expect that the lead-based glass is more reflective, and so it makes sense that that's going to be our core material. And then the cladding has a lower index. Okay, so that's how we're composing this system. So we have 2.5 as our n, 1.51 as our n prime, and if we use that critical angle and solve for phi c, we get inverse sine of n prime over n, and so that's 1.51 over 2.51. So take the sine inverse of that, and again, you want to make sure this is in degrees if you want this in degrees, and that gives us 37.2 degrees as our critical angle. So what that tells us is that if I want there to be total internal reflection, so I want it to reflect and not go into the cladding material, then my light source has to be at an angle of at least 37.2. So that's a pretty low angle. And so that is a pretty good system, right? So typically you would want this angle to be relatively small, so we don't have to have this at an extreme angle. All right, so let's repeat the same thing for determining what the critical angle for total internal reflection is for a fiber optic system. And the core refractive index is 1.52 and the cladding is 1.46. So the numbers are a little bit more a little bit closer together, and so we'll see how that influences the angle. And then also repeat the same calculation if we have the core and cladding of the same material that has a index of 1.47. So pause the video, do those quick calculations real quick, and we will check on what that is. All right, we're back. So let's take a look at what we have for this system, this fiber optic waveguide system. So again, the core has a index of refraction of 1.52, the cladding 1.47. Then we're going to repeat it where both of them have 1.47. All right. So again, I put this on here just to throw you off a little bit. Again, pretty simple sort of plug and chug. We're just looking for the sine of the angle is the ratio of the refractive indexes with the core and over the cladding. And so if I put 1.46 over 1.52, I get 0.96. Solving for phi, which is the critical angle, that's 74 degrees. So in this case, my critical angle is 74. So I have to at least aim the waveguide or the light source at an angle of 74 or higher to be able to get total internal reflection. All right, if I solve it again, but now I have 1.46 on both here, I'll end up getting that my angle in this case is 90 degrees, right? And so if I go back to the example here, let me show you this one. So here, this line is an example of the wave being 90 degrees. So effectively, what this is telling me by saying that my critical angle is 90 is it says that if I want my light to be totally reflected inside the waveguide, I have to fire it completely parallel to the core, and so it's not able to do anything. So this is basically not a good system for reflection. So this basically kind of expresses the need for having a cladding material that is less than the core material, because otherwise the only way to do it is have a light that's parallel, and as you might imagine, that's basically impossible to do.